Okay, so here, this is from the worksheet linked on the agenda, but we have this function f of x equals 2x squared plus 1. We want to find what the slope of the tangent line is at 2, right? This point P is what we're looking for. But to approximate that, we're going to look at different secant lines. So the first secant line we have will hit where x is 2 and x is 3. So we went ahead and found for Q1 is the other point, basically. So if this is P, so then Q1 would be up there, right? We're going to find the slope of that secant line. So plug 3 into the function, get 19. Then the slope is 19 minus 9 over 3 minus 2 to give us 10. Okay, then we do the second case here, with Q sub 2, which is closer. Right, so it should get the secant line should get a little bit closer to the slope of the tangent line, hopefully. So with this, when you put 2.5 into the function, you get an output of 13.5. Just be aware we're always looking at this point P is what we're interested in. So it's 13.5 minus 9 over 2.5 minus 2. That gives us a slope of 9. Okay, as we keep getting closer here, we have 2.1, 2.01, 2.001. You want to make sure you've tried this and you filled it out. So with this one, we get 9.82, and this slope is 8.2. 9.0802, it's 8.02. 9.8 or 0.08002 is 8.002. So as you see here, it sure looks like the slope is approaching something as these 2 points get closer together, correct? So if you can imagine if you actually tried to plot Q5, it's almost right on top of the point P, right? Barely there. So hopefully we can see it looks that the slope of the tangent line is going to be 8, right? As we keep getting closer and closer and closer, this is going to be 8, closer and closer to 8. Your calculator, when it does derivatives, does a similar process. It kind of looks at points on either side. We'll talk about that later. But this is how we can approximate that using a table. Now, the way that we're going to use this, today our goal was to find the derivative at a point. So let's go ahead and look at how we could algebraically do this using limits. Okay, so what we have is we're really interested in what the tangent line slope is at 2, correct? Now, we just can't use the same point twice, because if you try to do the slope formula with the same point twice, it's indeterminate. It's just 0 divided by 0. It doesn't work. But because it is indeterminate, maybe that kind of leads us towards, hey, maybe we should look at a limit here. So what we're going to do is we're going to take some other point out here, and we're going to call it x, right? It could be anywhere. I usually put it to the right. It just seems to make more sense for the definition. But what we actually do is if I have these 2 points, right? So the 2 points I'd have would be, again, this was where f of x is equal to 2x squared plus 1, right? So the 2 points I'd have is I would have 2, 9, and then the second point would be x, f of x, correct? And the thinking is we take these 2 points, and as they get closer and closer, as this point that has an x value of x gets closer and closer to 2, it should get, the secant line slope should get closer to the tangent line slope. So we take these 2 points, right, and we just set up a slope formula. So change in y, so f of x minus 9 over x minus 2, right? Just a good old slope formula. And we want to find the limit as x approaches 2. This is how we're going to find the derivative at a point. So with this, let's see what's going on with this limit. Well, f of x is this whole function here, correct? So let's replace it, and we get 2x squared plus 1 minus 9 over x minus 2, which we could simplify to be 2x squared minus 8 over x minus 2. At this point, I mean, even earlier, I guess, we could try direct substitution. Now if you look, if you put 2 in here, you get 2 times 2 squared, which is 8. 8 minus 8 is 0. Put 2 in the bottom, you get 0. So it's indeterminate, right? Which we know from working with limits just means that we have to do more work. Right? So what we're going to do next is, I think that it would be a good idea to factor this numerator, take out a 2, and then we can take the limit as x approaches 2 of 2x plus 2, x minus 2 over x minus 2. So we get the cancellation there, right? Those two factors cancel. We get the limit as x approaches 2 of 2 times x plus 2, right? Is everybody doing okay here? So really, once we wrote the limit, it's just the same thing we just finished doing, right? It's just writing the limit. It's kind of the new part. And then here we do direct substitution. We get 2 times 2 plus 2, which gives us 8, which that's what we thought the limit, the slope of the tangent line was going to be 8. So this would be, we could say the slope of the tangent line of, what was f of x? F of x equals 2x squared plus 1 is 8 at x equals 2. Right? So we need to know the function. We also need to know where on the function we're finding that slope at. Right? Obviously, if it's a parabola, the tangent lines are going to have different slopes in different locations. But for today, we're just looking at the slope of the tangent line at one particular point. So let's look more at that. Okay, so our definition of a derivative at a point I have up here. Now, we're going to have multiple definitions for a derivative. And really, you can use all of them for sort of all cases, whether it's at a point or just a general function. But just to kind of help us moving forward and just to kind of make it easier to understand, we're going to try to use this one when we're finding the derivative at a point. And then later, we'll look at a different formula we'll use for finding just the general derivative of the function. Now, when you're looking at maybe solutions on a Delta Math or MyMathLab, they might use different forms. It doesn't mean it's wrong, it just means there's different ways to do it. But I would say for now, associate this one with the derivative at a point, and then we'll do the other one for the general derivative. And then as you understand those, you can kind of interchange them and try to use what's easiest. So the derivative of the function f at the point x equals a is the limit of x approaches a of f of x minus f of a over x minus a. So it's just a glorified slope formula, correct? It's a limit of a slope formula. This notation, this is read f prime of a, or the derivative of f with a, but this is just prime notation. There were two people that discovered calculus at the same time in different locations. One of them used what's called prime notation. That was Newton. It was an appendix to a physics book, right? He wrote about calculus. He used prime notation. We'll talk more about different ways that can look. The other guy was a German mathematician named Leibniz. He used what's called differential notation. They both have their advantages and disadvantages that you'll want to become familiar with both of them. Because there are times where we'll need to use the differential notation. There's time where usually you use prime because it's quicker, like it's less writing. But sort of Newton was so smart and so ahead of his peers that a lot of people didn't really understand his explanation of calculus very well. So sort of continental mathematicians did better for a while there because they had what's called differential notation. This is f prime of a. This is just f prime, right? Or this could be x, whatever input. This is y prime. That's all prime notation. It means the first derivative. If you have two of them, it will mean the second derivative. Like you could just repeat and keep going. The other is called differential notation. With this one, when you do the limit here, we know that originally your definition for slope was delta y over delta x, correct? When you do the calculus, when you do the limit, the delta has become the letter d. So this is just saying, so dy over dx is just saying the change of y over the change of x. Okay? Sometimes you'll see it df over dx. F is just the name of the function, right? could be y equals, it could be f of x equals. Sometimes you'll see the d dx out here. This still means the change in f of x with respect to x is how we read this. So this one, you could just read it as dy dx, but probably better is the derivative of y with respect to x. Now we're going to get more into the notation and kind of see how we use it and how different things happen and when we start to mix up variables and stuff. But for now, just be aware there are two different notations. They mean the same thing. It's like f of x and y equals about the same thing all through algebra 1 and 2, right? Got used to it. Here, just the derivative of f at a, written f prime of a, is the slope of the tangent line at x equals a, right? And then also, f prime of a is the instantaneous rate of change of f of x at x equals a. So again, slope of the tangent line, instantaneous rate of change. If you ever see average rate of change, it means you're going to do like our warm-up and just use the old slope formula between 2 points. Pretty much now, since we're in calculus, if you see rate of change, it's going to indicate the instantaneous rate of change, the derivative. Okay, so for example here, we're going to find the slope of the tangent line of y equals radical x at x equals 4. Then we're going to write the equation of the tangent line and the normal line at x equals 4. Normal just means perpendicular to the tangent line. The normal line is perpendicular to the tangent line. This is where the point slope form of an equation really shines, because if you have the tangent line and point slope, all you have to do is change the slope and you have the normal line. You don't have to do any calculations at all, just change one number. So I would recommend, as you're learning this, since it's new to us, is that we just really work on writing out the formula and use our notation. Okay, so we have that we're going to find y prime at 4. Right? Here I had y equals, so we could use y. Or we could switch it and say that this is f of x, if that makes you feel better. So we're kind of going to mix them up here. But our definition was the limit as x approaches 4, right? That's the number. Well, here, I'm sorry. Let's write the whole rule out, and let's try this way. So we had f prime of x, or f prime of a, is, okay, so f prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. That's just our general form. Okay, now, with our equation over here, or with our property over here, what we're asked to do, we can see the function is going to be the square root of x, correct? And we can see that we want to find it at 4, so that means a is going to be 4. We're going to leave x in here and have to simplify it and do the limit. Okay, so what we'll get here is that f prime of 4 will be the limit as x approaches 4 of f of x minus f of 4 over x minus 4. So the way I would do these now as we're learning it, I would write this formula out exactly with the a's and the x's in it. Next step, I would say, well, where am I looking? It's going to tell you, look at x equals 5 or x equals 10 or a equals 6. But I'm going to take that number and put it in for all of the a's. Right? So all the a's became 4. Okay. Now from here we can evaluate. So f of x we know is just the square root of x, correct? So let's see, we'll get the limit as x approaches 4 of radical x minus radical 4 over x minus 4. So again, I replaced f of x with the square root of x, and that became the square root of 4. You do need to write the limits out here. We're proving these, or we're finding these slopes of tangent lines using the limit definition of derivative. If you happen to know some derivative rules, which some of you probably do, we don't get to use it yet because we're using the limit definition. So we have to go through this process. It's really not about finding the answer. There's a lot easier ways to find the answer. We're working on the process here. So with this, let's simplify a bit. Limit as x approaches 4, radical x minus 2 over x minus 4, square rooted 4. Well, here, hopefully, as soon as you saw a square root minus something, you thought, hey, I bet the conjugate, well, I'm remiss. I should say we should have tried direct substitution. Direct substitution will always give you indeterminate if you set it up right with these limits. Right? It'll always, if you look, you get radical 4 minus radical 4, which is 0. You get 4 minus 4, which is 0. So it's always going to do that, but we probably still should check. And I guess if it didn't, it would mean you wrote something down wrong. But here we're going to use the conjugate. So we have radical x minus 2 and then radical x plus 2 on top and bottom. Right, I just multiplied the top and the bottom by the square root of x plus 2. Again, it creates that difference of 2 squares pattern in the numerator. Remember, don't distribute the denominator. This thing should cancel out. That's what's going to happen here. So let's see if that happens. And that's going to give us that f prime of 4 is the limit as x approaches 4. If we get x minus 4 on top, x minus 4 times radical x plus 2 on bottom. So those two factors will cancel. Don't forget when that happens, we get a 1 on top and then radical x plus 2. Okay, now we're ready for direct substitution. Remember, once you substitute, you stop writing limit. Just like once you square root 25, you stop writing the square root sign, you just put 5. So here we're going to say 1 over radical 4 plus 2, which gives us 1/4. So f prime of 4 is 1/4. So that means the slope of the tangent line at 4 for this function is 1/4. Does that work so far? Okay, now let's look at how we're going to write the equation of the normal line, or the tangent line. So to write the equation of the tangent line, we're going to use our point slope form, right, which was y minus y1 equals m x minus x1. Well, we know the slope is right here, correct? So the point at 4 on f, we had 4, and then it was 2, right? Just based on the original function, right? Because the original, our point is 4, 2, because this is the square root of 4. The original function was just the square root function. So that means that for our tangent line, we're going to get y minus 2 equals 1/4 x minus 4. Don't distribute, just leave it. Okay? If you would have to type this in your calculator, which is kind of a nice thing to do sometimes, just type y equals 1/4 parenthesis x minus 4 plus 2. Your calculator takes care of it. The normal line, we said, is perpendicular to the tangent line. So it's still y minus 2 equals, but it's going to be negative 4, and then x minus 4. Right, so it's exactly the same, except the slope is the opposite reciprocal. Okay, for our next example, this was number 9 from the attached worksheet there. It was for the function y equals x squared, what is the slope of the tangent line at x equals negative 2? And then also, what's the equation of that tangent line? And then what is the equation of the normal line, which is perpendicular. So what you might note is that the point here that we're looking at on this function, it's the ordered pair negative 2, 4, correct? That's f of negative 2 or whatever. So to do this, we're going to get f prime of a, again, as the limit as x approaches a, f of x minus f of a over x minus a. It's really good to get this formula memorized now. Again, we want to use this for now for finding the derivative at a point. It's just nice to have it before we look at a different formula, right? There's another one we're going to look at, and you don't want to get them mixed up. So we're going to say f prime of negative 2 is the limit as x approaches negative 2. And f of x would just be x squared, correct? Just the function. And then f of a would be the output of the function, right, when we plug in -2, which would be 4. Then on bottom we get x minus -2. Right, just be careful there. Right, so this point here is actually f of -2, or f of -2, and then -2 is the a value there. So then from here we can factor. So x plus 2, x minus 2 in the numerator, x plus 2 in the denominator. Right, so once we do that, those cancel. So then f prime of -2 is the limit as x approaches -2 of x minus 2. And with that, we can go ahead and do direct substitution. And we get that f prime of -2 is equal to -4. So now that's going to be the slope of our tangent line, correct? So when I'm going to write the tangent line, we're still going to use the point on the graph, which was -2, 4. And then we're going to use a slope of -4, because that was the derivative of f at -2. So here our point slope form of a line, y minus y squared is m times x minus x sub 1. Use this formula and leave it in this formula. It's such a waste of energy to not do that. It's right here for you. So we'll get y minus 4 equals -4 x plus 2. That would be the tangent line. Again, I did x minus -2 and plus 2. And then for the normal line, again, we have the point -2, 4. This time our slope will be the opposite reciprocal of -4. So opposite makes it positive, reciprocal makes it 1/4. And we just get y minus 4 equals 1/4 x plus 2. So that was how we would do number 9 there. So here's number 11. I want to take a chance to do a rational function because they're a little different. Right? All the quadratics are kind of the same. They just kind of work out the same way. So for this one, our goal is, if we want to find f prime of a, we know that's the limit as x approaches a of f of x minus f of a over x minus a. Probably the most important part of the problem is knowing the formula, right? You can be really good at algebra, and if you have the wrong formula, it's not going to go very well. So then f prime of 2 is the limit as x approaches 2 of f of x minus f of 2 over x minus 2. Okay, so we just have to evaluate this. And again, we could find that this point up here was what, 2? Well, here we have to find it, don't we? So if we look at this function, we see that f of 2, because we need to find that, we'll put a 2 in here. We'll get 1 divided by 1, which is just 1. So that's our point. This is called our point of tangency. It's where the tangent line hits, right? The point 2, 1, it's where the tangent line is going to hit. Now, we don't know what its slope is yet, but we know where it's going to hit. So if you had to write the equation of the tangent line at this point, you already know 2 of the 3 pieces of information you need. So, you know, that's something good. If that's all you can find, I mean, you got 2/3 of it, right? So let's see, f of x is 1 over x minus 1 over x minus 2. Again, I just replaced the function f of x with 1 over x minus 1. We said f of 2 was 1. That's just from the original function. The denominator is still x minus 2. Here, it's a complex fraction, so let's get a single fraction on top. We'll need a common denominator. There's a bit of a trick here that we have to watch out for. Not a trick, but now let's show you. So here we multiply 1 by x minus 1 over x minus 1. Right, so we just multiplied 1 by x minus 1 over x minus 1 to get the common denominator. This negative, though, will distribute into the numerator. And that is where people miss this a lot. So I would recommend, especially early on here, writing this as limit x approaches 2, 1 minus x minus 1 all over x minus 1 over x minus 2. So go ahead, I went ahead and wrote it as a single fraction before I distributed. So from here, we get 1 minus x plus 1 over x minus 1 over x minus 2. Again, if you're at all having trouble, as many steps as you can show is more helpful. Well, we know 1, we got that, right? We get the limit as x approaches 2, we get 2 minus x over x minus 1 over x minus 2. At this point, I'm ready to multiply by the reciprocal. For a lot of people, it may really be helpful to write x minus 2 as a fraction and just put it over 1. Just to remember that then when I multiply it, it's going to be the, take the reciprocal. So the limit as x approaches 2 of 2 minus x over x minus 1 times 1 over x minus 2. Now we know we need stuff to cancel if this is going to work. Nothing cancels immediately, but if we look, we have 2 minus x and we have x minus 2, which are opposites, right? So you might know that if you cancel opposites, it kicks out a -1, or you could actually factor out a 1 here and get x minus 2 over x minus 1 over x minus 2. So you could have factored a -1 out of that top also. However you want to think of it though, these two cancel, correct? So we're left with the limit as x approaches 2 of -1 over x minus 1. And at this point, we can go ahead and plug in with direct substitution. So we'll get -1 over 1. So that gives us that f prime of 2 is going to be -1. So that's going to be the slope of our line, correct? So for our tangent, right, we had the point 2, 1, which is all the way back here, right? That was our point of tangency. We have a slope of -1. So y minus 1 equals -1 x minus 2 would be your tangent line equation. For your normal, it's the same point. The slope is the opposite reciprocal, which is just 1. So y minus 1 equals 1 times x minus 2.